Howdy. This video is on nuclear reactions. Nuclear reactions describe important processes that occur in stars, bombs, nuclear power plants, and nuclear medicine. After the Big Bang, there was just hydrogen and helium, a little bit of lithium. All the other elements were produced by nuclear reactions that occur in stars. And so after watching this video, you should be able to balance nuclear reactions. You should be able to determine if an isotope is stable or unstable based on its number of protons and neutrons. And you should be able to predict the type of decay a radioisotope will undergo. And so chemical reactions, you have a rearrangement of atoms. You have forming and breaking of chemical bonds. It's all about the electrostatic interaction. Nuclear reactions, elements or isotopes of the same elements are converted from one to another. Protons, neutrons, electrons, and other fundamental particles may be involved. Because nuclei are kept together by the strong force, nucleons are kept together by the strong force, nuclear reactions can involve much greater amount of energy. Because chemical reactions change electrostatic interaction, chemical reactions are accompanied by absorption or release of relatively small amounts of energy. Rates of reactions are normally affected by temperature and pressure. For nuclear reactions, again, because you're involving the strong force, nuclear reactions can accompany absorption or release of tremendous amounts of energy. Rates of a nuclear reaction are not affected by temperature, pressure, and catalysts. And so we can talk about 6 different nuclear reactions. We can talk about alpha emission, beta emission, positron emission, electron capture, induced nuclear fission, and nuclear fusion. Now these are not the only nuclear reactions, but these are the only ones that we'll talk about. The ones in blue are radioactive decays and follow first order kinetics. The math that is involved when we talked about first order kinetics during chemical reactions is the same math that we can use for radioactive decays. And so emission decay means the radiation is a product. And so alpha emission or alpha decay is the same thing. I'll use emission and decay interchangeably, but alpha emission means that the alpha particle is a product, or alpha decay, the alpha particle is a product. Beta emission, beta decay means the beta particle is a product. Positron emission, positron decay means the positron is a product. Electron capture is a little bit different. The electron is actually a reactant. The sums of the mass numbers and the sums of the charges on the reactants and product side of the equation must be equal. So that's how we balance nuclear reactions. And so if we look at this nuclear reaction, we have boron going to boron 12 going to carbon 12 plus a beta particle. And so again, the charges have to be the same products reactants. And so boron has 5 protons in the nucleus, so it has a +5 nuclear charge. Carbon 12. All carbon atoms have 6 protons, which is a +6 charge of the nucleus. The beta particle's electron has a -1. So 6 minus 1 gives us 5. And so we see for this reaction that we have the same charge on the products and reactant side. Now the top number is the mass number, and so 12 and 12. And so we have the same mass number products and reactant side. Now if we think about it, the boron, again, its atomic number is 5, so it has 5 protons. And 12 minus 5 means it has 7 neutrons. At least boron 12 will have 7 neutrons. Now carbon has 6 protons. Carbon 12 would have 12 minus 6, 6 neutrons. And so during this reaction, what's happening is boron is changing into carbon. You could also think about it as a neutron changing into a proton. And if a neutron is changing into a proton, it means that a down quark is changing into an up quark. And so again, for this nuclear reaction, we can think about it in 3 levels. We can think about a down quark changing in an up quark, which means the neutron changes into a proton, which means boron 12 is changing into carbon 12. Now the beta particle, which is a high energy electron, so the high energy just means it has a lot of kinetic energy, was created when the down quark changed into an up quark. And so the beta particle is actually created in the nucleus. And so again, please remember, in balancing nuclear reactions, you got to make sure that the products and the reactants have the same charge, the sum, and that the products and reactants have the same sum of the mass numbers. And so we have this nuclear decay, cobalt changing into nucleus. It's an example of which of the following. Now, to find out what is formed, all we have to do is make sure everything is balanced. And so we have a mass number 60, mass number 60, and so that means what's being formed will have a mass number 0, 27, 28, and so whatever's formed is going to have a -1 charge, which would mean it's going to be a beta particle. So to figure out what is formed or what type of decay is occurring, you just make sure that the nuclear reaction is balanced. So for this one, we have 222, 218. And so the mass number of what's being formed is going to have 4. 86, 84. So the charge of what's formed is 2. And so that would correspond to alpha particle. And so this would be an example of an alpha decay. How many neutrons are produced during this reaction? And so again, all we have to do is balance it. And so 246 plus 12 gives us 258. 258 minus 254 gives us 4. Notice that the charge in this case doesn't really matter because 96 plus 6 is 102. So we have 102. This is 0. And so for this one, there should be 4 neutrons. And so we can do this for all of them. And so we have 239 plus 4. That gives us 243. And so that top one would be 1. 241 plus 4 is 245. Minus 243, so that would be 2. 242 plus 4 is 246. And so that's 1. 253 plus 4 is 257. 1. 246 plus 12 gives us 258. And so that would be 4. And so again, all we're making sure is that the mass number is the same product's reactant side. We're not worrying about the charge because the neutron has 0 charge. And notice that 96 plus 6 gives us 102. And so the charge is already balanced. 252 plus 10 is 262 minus 257. So that gives us 5. 249 plus 12 gives us 261. 261 minus 257 gives us 4. And so a stable isotope is one that does not spontaneously decompose into another one. And so again, spontaneous means occurs without any outside intervention. Doesn't mean it happens instantaneously or quickly. It just means it occurs without any outside intervention. A radioactive isotope is one that spontaneously decomposes into another nuclide. Now there are 6 rules of thumb for helping us determine which isotopes or nuclides are stable and which ones are not. So the first one is that the number of neutrons is equal to or greater than the number of protons, except for protium, which is that isotope, or helium-3. And so what we'll see in a little bit is that if you plot the number of neutrons versus the number of protons, for the first 20, it's a 1-to-1 ratio, and then the number of neutrons has to increase. Up to atomic number 20, number of protons and neutrons are equal. Above 20, the ratio of neutrons and protons increases. The zone of stability contains all stable nuclides, but some nuclides in this band are unstable. And so here we're plotting number of neutrons versus number of protons. And so for the first 20, it's a 1-to-1 ratio. Now the blue is your band of stability. And so this contains all the stable isotopes, but some of the ones in this band are unstable. And so if we zoom in here, we'll see the red ones are actually unstable, but all stable ones are in this band. Certain numbers of protons and neutrons called magic number confer unusual stability. So 2, 8, 20, 26, 28, 50, 82, 126. And so if a nuclide has 50 protons, 50 neutrons, it's going to be a little bit more stable than you would expect otherwise. Technetium, promethium, and all elements beyond bismuth have no stable isotopes. Nuclear stability is greater for nuclides containing even numbers of protons or neutrons or both. And so again, everything after bismuth is radioactive, and technetium and promethium have no stable isotopes. And so the ones in red, there are no stable isotopes. And just to remind you, everything after uranium, so uranium's here, is man-made. So you go from there and then from there. Now it's kind of interesting. Even numbers are more stable than odd numbers. And so the number of stable nuclides with even number of protons and neutrons is 157. With odd numbers of protons and neutrons is 4. And again, if you think about electrons, electron orbitals, electrons tend to be paired and are in shells. And for nucleons, you have the same type of idea. If we went more in depth into nuclear structure, we'd see that the nucleus is also in shells. So by what process will lithium-9 decay? And so the way I like to do it is to determine the number of protons and neutrons. And so lithium is element number 3. And so that means we have 3 protons. And 9 minus 3 gives us 6 neutrons. And so remember, for the first 20, the number of protons and number of neutrons should be about 1 to 1. And so here we have too many neutrons. And so what we should expect is that a neutron will change into a proton. You can also think about relative to the band of stability. So here's our protons, here's our neutrons. And so we're on this side of the band of stability. And so that means this should be beta decay. And so again, you can think about it either way, that because it should be 1 to 1, a neutron will change into a proton. And so if you balance that, you'll see that it has to be a beta decay. Or you can compare it to the band of stability. If it's on this side, it has to be a beta decay. By what process will oxygen 14 decay? And so again, we look at the protons and neutrons. And so each oxygen atom has 8 protons. 14 minus 8 gives us 6 neutrons. And so that means the protons are going to change into a neutron. It also means that we're down here. And so that would be positron emission or electron capture. And so here, if oxygen 14 goes to electron capture, we balance it, so we'd end up with 14. 8 minus 1 gives us 7, so it would be nitrogen 14. If we have positron emission, 14 plus 0 gives us, or minus 0 gives us 14. 8 minus 1 gives us 7. And so positron emission and electron capture, we can't really distinguish between the two in this course. And so if it's ever positron emission, it can also be electron capture. And so during both of these processes, a up quark changes into down quark, which means a proton changes into a neutron. By what process will curium-247 decay? And so remember, everything after bismuth is radioactive. So if we're looking at the periodic table, we see that curium has 96 protons. And so 247 minus 96 gives us 151 neutrons. This is just way too big to be stable. And so what's going to happen is undergoing alpha decay. And so using your band of stability, if it's up here, it's alpha decay. If it's over here, it's beta decay. If it's below the band of stability, it's going to be positron emission or electron capture. And so we'll consider that all isotopes with more than 83 protons are unstable and will undergo alpha decay. And so if we look at 247 minus 4, that gives us 243. 96 minus 2 gives us 94. And so element 94 is plutonium. And so if you're up here, you have more than 83 protons, you'll undergo alpha decay. If you're above the band of stability here, it's going to be beta emission. Down here, positron emission or electron capture. And so elements can be converted from one to another. Fundamental particles may be involved. Nucleons are kept together by the strong force. Nuclei are kept together by the strong force. Because the strong force is much stronger than the electrostatic interaction, nuclear reactions can absorb and release tremendous amounts of energy. Rates of a nuclear reaction are not normally affected by temperature, pressure, and presence of a catalyst. Make sure when you're balancing nuclear reactions that the charges add up to be the same for the products reactants, and the mass numbers add up to be the same for the products and the reactants. I hope that was helpful.